This podcast is brought to you by HEC Paris.
My name is Loriano Mancini. I will be chairing this session. And the first speaker is Veronica Zeller from HEC Paris, who is the local organizer here.
Thank you, Loriano. I'll just take the remote control. So this is I will present a paper on the efficient estimation of learning models, which is a joint work with my fellow co-organizer, Laurent Calvet. So in financial markets, investors typically do not observe the state of fundamentals, or if you want, the state of nature, but must infer it from available data. And this sequential learning process has profound implications on asset prices, portfolio choices, for example. And let me show you the learning structure. We have the econometrician, who does observe neither the state of nature nor investors' beliefs. And well, typically, the econometrician would like to estimate both the state of nature and the investor beliefs. But unfortunately, these learning models are very difficult to estimate. They do not have closed form likelihood functions. So in this paper, we propose a method of doing this, and we are able to estimate, to impute the state of nature and investor beliefs. Moreover, we are even able to estimate information quality of investor beliefs. The outline of my talk will be the following. I will present the three main contributions of the paper, mainly estimation of learning models, filtering, and the introduction of dynamic hypothesis testing, which can be applied, for example, to test rational expectations hypothesis. Then we will move to an application. We will take the example of Markov switching representative agent economies, and we will apply it to a long series of daily US equity data. And I will conclude. So let me go back to this schematic, to the learning structure, and let's introduce some notations. I will denote by MT the state of nature, by pi t investors' beliefs about the state of nature, and so the investor prices assets. And so the econometrician observes something else. He observes returns or another type of data, and he would like to impute the state of nature and investor beliefs. Now let's introduce some assumptions. So we suppose that the state of nature is a Markov chain with the possible states. The investor receives a signal at each date t, we denote it by xt, and we suppose that it has a known PDF, a conditional PDF, given the state of nature. As I said, we denote by pi t investor beliefs. So pi t j is the probability that MT is in state j, given the fundamentals by date t, the signal. Now, the state of the economy consists of both the state of nature, MT, and investor beliefs, pi t. And so this is first of the Markov process, and you look at the state space is quite large, and now this will be the problem for the estimation, because now the econometrician observes another type of data, say returns, and since we know that investors prices assets, it's a reasonable assumption to assume that returns are functions of investor beliefs only, not the true state of nature, but investor beliefs and the signal xt. And we assume that this has a closed form PDF conditional on the state of the economy. Now we would like to estimate. So suppose that this is this PDF has parameter theta, which is a p-dimensional parameter, and we would like to estimate this theta. Now the problem is that because we have this large state space, we cannot the likelihood function is not available in closed form. So we cannot apply a likelihood-based approach. Now, what we will do is the following. We will indirectly use the likelihood function from the full information model. So what is what happens in the full information case? Investor is God, so he knows the state of nature. And so let's go back to the previous slide. Since he knows the state of the economy reduces to MT only. And hence the state space is finite. And in this case, the likelihood function is available in closed form. So denote this likelihood function by L, and it depends on a parameter phi. Then, so what we will do is that we'll estimate our the structural parameter of the learning model by using indirectly the likelihood function from the full information model. And how can we do this? By using indirect inference. So let me show you how does this estimation work. Indirect inference has been introduced by Gourieroux, Montfort, Renaud, and Smith. And it's based on the idea of, it's based on the choice of an auxiliary estimator. Denote this auxiliary estimator by mu tilde. Say that in our case, for the moment, suppose that this auxiliary estimator is the maximum likelihood estimator from the full information model. In the first step, we use our data to estimate this auxiliary parameter. In the second step, we simulate data from the structural model, in our case it's the learning model, and we calculate the same type of auxiliary estimator but using the simulated data. And so this, just a notice that here we have the size of the simulated data is larger than the size of the original data. And finally, the indirect inference estimator is the one that minimizes the distance between the auxiliary estimators, the one computed with real data and the one computed with simulated data. Now, one necessary condition for the indirect inference estimator to be well defined is that the dimension of the auxiliary estimator needs to be at least as large as the dimension of the structural parameter. Now, typically, in learning models, this is not the case. We may have more parameters in the learning model. So what we do is that we extend, so denote by phi hat t the maximum likelihood estimator of the full information model. We extend this auxiliary estimator by a set of sample statistics. Which one do we choose? Those that quantify the features of the data that the learning model is designed to capture. We will see later on in some examples. Now, so now you have an idea how to estimate a learning model. We can use indirect inference to estimate the structural parameter. Now, what else? The second contribution of the paper is that we introduce a filtering. Once we have the estimate, we introduce a filtering method to impute the state of the economy. So since the state of the economy is first order Markov, we can use a particle filter, and we actually use the sampling importance resampling algorithm. And once we have what can we do with this? Once we impute the state of the economy, we can actually simulate the likelihood function. We can estimate the likelihood function via simulation, and we can use it for specification tests, right, to do model selection, and we can also forecast returns. Now, the third contribution of the paper is the dynamic hypothesis testing. We are interested. The goal is to introduce a test concerning moment condition using the hidden state of the economy. And this is the test statistic that we use. So what is S here? ST denotes the particle filter at the end of day t. And phi bar is the sample mean of the phi's evaluated at each particle. The phi defines is the function that defines the moment condition. Now, so the statistic is just phi bar divided by the standard deviation of phi bar given st minus 1, the particle at day t minus 1. Now the problem is that these phi ends are not IID, so the sample variance is not a consistent estimator for this variance. And we estimate this variance by simulation by using the standard error on a number, say uppercase P filters. All right, we'll see how can we apply this in empirically. Now, this dynamic test can be used, for example, to test the rational expectations hypothesis. By the law of iterated expectations, we can show that this equation holds. That the probability that the state of nature is in state J given data till t minus 1 is equal to the expected value of investor beliefs given RT minus 1. Now we can use you can use this test to test this null hypothesis choosing the appropriate phi function for this. In this case, the phi would be equal to pi t minus mt. Right? All right. Now, actually, it would be pi t minus the indicator function of mt equal to mj. All right. Let's consider an example. Here we consider an example of regime switching Lucas tree economies. We suppose that the signal consists of consumption growth, dividend growth, and noisy signals of about the state of nature. So here the epsilons in the consumption growth and dividend growth are correlated. They are Gaussian with zero mean and variance equal to 1, and the correlation coefficient is denoted by rho CD. And in the delta t, in the signals about the state of nature, we have a parameter sigma delta that controls for information quality, and ZT is IID normal. Now we suppose that the investor is Bayesian, and he has an 8 times invalid utility function. So he can compute iteratively the pi t's using his previous beliefs. Now, if we consider the case when sigma delta is equal to 0, it means that, remember, so we are back to the full information case where investor is God, so he knows the state of nature, and we know that in this case we have closed form likelihood function. Now, in this particular case, the PD ratio, suppose that we know the state of nature, say that it's is the state mj, then the PD ratios that we denote by qmj can be calculated via a linear fixed point equation. And under learning, this is not the case anymore. It's actually linear in the beliefs. The price differentiation is linear in the beliefs. Now the return equation, the log SS return equation is the following: the drift depends on both pi t and mt, but the volatility only depends on mt, right? The state of nature. Now, how should we need to choose an MT process as well, and we choose it such that it satisfies two properties. We would like to fit a long series of daily returns, so it will have a large state space, and we would like to capture volatility dynamics on a wide range of horizons. And we know that the Markov switching multi-frequency MSM modeled by Laurent Calvet and Daniel Fischer satisfies both properties. So let's see how it is defined. It's defined in the following way: MT has K bar components, and M1 corresponds to the most persistent component, and the K bars component corresponds to the most transitory component. And they are defined in the following way: a date T with probability, let's start with this one, probability 1 minus gamma K, we stay where we were in the previous state. And with probability gamma k, we redraw a new value from a Bernoulli distribution with equal probability with states m0 and 2 minus m0. What is m0? M0 is a parameter between 1 and 2, and these transition probabilities gamma k are defined defined by two parameters. Gamma k bar corresponds to the probability of the most transitory component, and b is the spacing parameter. Now b needs to be greater than 1. The dividend volatility is now the product of all these k bar components times a constant, and now we will focus in this paper. We focus only on the parameters of specific to MSM, and we calibrate all those that are specific to consumption and dividend growth. Now, how do we let's revisit indirect inference. We said that we can choose the full information maximum likelihood estimator as auxiliary estimator, but here we have, in this case, how many structural parameters do we have? We have 4, and in the full information case, we only have 3. Sigma delta controls for information quality, and this is the parameter specific to the learning model only. So we need an extra statistic to extend our auxiliary estimator, and we will choose the one that we said that we'll choose something that a statistic that quantifies features of the data, and that the learning model is designed to capture. So here, this learning model is designed to capture skewness. So we choose a statistic that quantifies the skewness. It can be the third moment, but in this case, we can even choose the sample median because, in fact, I did not tell you before, but in this model, the price-event ratio, the average price-event ratio is fixed to 25, say in yearly units. And because of this, the expected value of the returns does not vary with theta. So since the mean is fixed, the median is also a measure for skewness. And actually, this will be our choice, the sample return median, as opposed to the skewness, as opposed to the third moment, and to explain this choice, to convince you of this choice. Let me show you some box plots. So here you have box plots for the 4 parameters of this learning model. We have m0, gamma k bar, b, and sigma delta. And the first box plots correspond to moment-based approach. To specifically, this is an SMM, simulated method of moments, when we choose the 4 moments that fit the best. I can show you later how we chose the moments. These are the second, third, fourth, and leverage. And the second and third box plots correspond to indirect inference estimators with the full information maximum likelihood extended by here the third moment, and here extended by the sample median. And what we can see is that, especially here in the last plot, here in the last box plot, we can see that we have a big efficiency gain when choosing the indirect inference estimator with the full information maximum likelihood estimator extended by the sample return median, as opposed to the one with the third moment. Right. So this was for this is a simulation study. Here we have 3 components in the MSM. Sample size of 20,000, and the size of the simulated data is 10 million. Let's see the empirical application. So here we have daily log SS returns from 1926 until December 2009. And we will actually use just part of this data until the December 99, because we will do some forecast exercise for the last decade. See, these are the estimates, the indirect inference estimates in this part of the table. You can see the indirect inference estimates for various number of components in the MSM. And what we can see is that sigma delta, so in parentheses you can see the standard errors. And here we see that sigma delta is decreasing, but for all specifications, in all specifications, it's significantly different from 0, and we have that's why we obtain actually higher likelihood, estimated likelihood functions than the full information case, where we would have sigma delta equal to 0, right? And here we have the moments that are calculated under these specifications. All right. Now we do a Hec-adjusted Wong test for the model selection, and so far it's with k bar equals 4 that we obtain the highest likelihood function, and these are significantly different from the other specifications. Now here we have the forecast exercise. So we reported failure rates of the value at risk forecast, and here we compare our method to two classical methods. The historical simulation, historical value at risk is here. We computed the value at risk for both 1-day and 5-day horizons, and here we have the 1%, 5%, and 10% level. We did the same exercise with the student Gauge 1.1 and with the full information model with the 4 components and imperfect information learning model with the 4 components. And what we can see is that, so in bold you have those that are significant, the forecasts that are significantly different from their theoretical values. So you can see that the Gauge failed 6 out of 6 times, right? Full information failed 4 out of 6 times. And the imperfect information failed only once out of 6 times. So this clearly, and historical value at risk was just twice out of 4. Here we couldn't make 1% level. So in any event, the imperfect information forecasted the best, the value at risk. Now let's do something that we cannot do with, so until now we just compared the performance of learning models when compared to reduced form models. But let's do something that we cannot do with reduced form models. We will use we will impute the beliefs, the state of the economy, and we will test the rational expectations hypothesis, which is rational expectation hypothesis using the price event ratio. So we will see that if this, let's see if this holds. So Q pi is the one imputed by the investor, and QM is the one computed by the mathematician. So here are the returns for a particular. So here we are in 1929, right? And we have the log FS returns, and here we have in black the expected price event ratio Q pi, and in red we have the same but for QM. And you can see that we have in most of the cases this hypothesis seems to hold. Now we still have some wedges that appear, in particular in the fall 1929. And if we magnify this, then we can see this big difference even better. And how can we explain this? Let me remind the return equation. This can be explained by the fact that when the wedge appeared on a day when we observed a large positive return after a large negative one, and this can be explained from the point of view of the investor. It can be explained only by having a high Q pi, while the volatility is still high. So a mathematician infers that the price event ratio is low. Now you would think that this is okay. This is just our model, our estimation. But if you look at the newspapers at that time, in October 1929, we had these kind of sentences. This is the time to buy stocks. Buying of sound seasoned issues now will not be regretted. The investors were indeed over-optimistic about and they overpriced the assets, right? Now let's see if these differences are significantly different. If we have significant differences by using our dynamic test, hypothesis test. So for this is the magnified period, fall of 1929, and here we have the So this is the magnified part from the previous slide, and here we have these pseudo z-stats of our dynamic test, and here are just the critical values, right? So we have significant differences mainly in the between October 1929 and the end of December 1929. And in red, you can see the returns that had been detected as giving significantly different results between QPI and QM. All right, so this is where I wanted to conclude. We have three main contributions. We introduced a method to estimate learning models via indirect inference. We are able to impute fundamentals and investor beliefs from market returns. And we developed a dynamic test involving the hidden state of the economy, and we can assess the rationality of investor beliefs. We actually used in the paper these results to design. We use this mispricing to design a trading strategy when we observe significant differences between the QPIs and QMs. When the investor is over optimistic, then our risky share is we stay out from the market. Risky share is equal to 0, and when is the opposite case, that this black line is below the red one, and we have significantly different results, then it means that the investor is over pessimistic. So our risky share would be equal to 1. All right, and so this is just an example of application of this rationality test. Now, we also have good empirical results when applied to a long series of daily aggregate equity excess returns. All right, so thank you for your attention.
Please visit us at www.hec.edu.